Today we're going to introduce a fourth quantum number. It wasn't one of the original ones that Schrodinger thought of, but it is one that came along later on. It has to do with a property called spin. Now, spin is really a wave phenomenon, but there's a particle interpretation that we're going to think about. Charged particles, like electrons, when they're on a curved path, create magnetic fields. When you were a kid, maybe in a science class or as part of a project of some kind, you may have created an electromagnet by winding wires around and around. If you take your fingers of your right hand, this is called the right hand rule, you take the fingers of your right hand and you point your index finger in the direction of the electron travel, where the electrons are going, and you curve them in the direction that the curved path is following, your thumb will point towards magnetic north. Well, an electron is a charged particle, and electrons are spinning around, which means they're on a kind of a curved path. Well, there are two possible ways that this could be, that the electron could be spinning, compared with an external magnetic field. If it's spinning one direction, magnetic north will be down. If it's spinning the opposite direction, magnetic north would be up. And so there are two spins, if you will. So as the electrons spin, their magnetic fields have two relative orientations. And this fourth magnetic quantum number is called the spin quantum number, and it represents which direction is the spin. It only has two possible values. One is plus 1/2 and the other one is minus 1/2 for spin up and spin down. Now this guy, Wolfgang Pauli, came up with this Pauli exclusion principle. He discovered that no two electrons in the same atom can have the same four quantum numbers. So that now includes N, the principal quantum number, L, the secondary or orbital quantum number, M sub L, which is the magnetic quantum number, and now this one, M sub S, which is the spin quantum number. Here are the consequences of that for electrons that are in the same atom. Any two electrons in the same orbital have to have opposite spins. Here's why that's true. If they're in the same orbital, then their N is the same, their L is the same, they're in the same subshell, their M sub L is the same because that's what designates an orbital, and if one of them has an M sub S that's plus 1/2, the other one has to have M sub S equal to minus 1/2, or all four quantum numbers are the same because these three are all identical for the same orbital. Another consequence is that the maximum number of electrons then you can have in any orbital is 2, because there are only two spins. So if you have a spin up one in there already, then the next one has to be spin down, and then it's full. You can't fit any more electrons in there. So if we think about our various subshells and what their populations could be, well, the S subshell only has one orbital. And since there's a maximum of 2 electrons per orbital, our maximum electron population in the S sublevel is 2. A P subshell has got 3 orbitals. Remember, this is the one that's got these dumbbell-shaped ones that are 90 degrees from each other. You have that orientation. Well, if there are 3 orbitals, each one can have 2 electrons in there. That means the maximum population is 6. With Ds, we found that there were 5 orbitals. 2 electrons each gives a maximum population of 10. And Fs have 7 orbitals, and so that gives a maximum population of 14 electrons. The Aufbau Principle comes from a German word that literally means building up. The Aufbau Principle says that electrons fill the atom from the lowest possible energy sublevels to the highest energy sublevels or subshells. This graph here gives us an idea of how this works. This is an energy diagram. So as we go up in the y-axis, we're plotting energy. The lowest of all sublevels, as you can see here, is the 1s. The first electrons that go in any atom are going to go there in the 1s sublevel. Now we're starting to deal with polyelectronic atoms. These are atoms that have more than one electron. So in other words, they could be something other than hydrogen, basically. So if you have more than one electron, you know that this 1s sublevel could contain the first 2 electrons, but then it would be full, because according to the Pauli exclusion principle, there's a maximum of 2 electrons in an s sublevel. The next level, the next shell, n equals 2, has 2 sublevels, 2s and 2p. 2s turns out to be a little bit lower than 2p in energy, and so the next 2 electrons would go in the 2s because it can have a population of 2. And then the next 6 electrons could go in the 2p. Next shell, n equals 3. That has 3 subshells, 3s, 3p, and 3d. And s is a little lower than p is a little lower than d. The higher the letter number, the higher the energy in these split levels. Well, a 3s can have 2 electrons in it, a 3p can have 6, and a 3d could have 10. So the maximum populations that we'd see is we could have 2 here, we could have 2 and a 2s, we could have 6 and a 2p, this could have 2, this could have 6, and a 3d could have 10. So for hydrogen, where would the electron be in hydrogen? Well, if it's a ground state hydrogen, in other words, one that hasn't been excited, hasn't been given any extra energy, that one single electron is going to go here in the 1s sublevel. How about helium? Well, helium is got 2 electrons in it because it's element number 2. So that means those 2 electrons could both fit in the 1s because s's can contain up to 2 electrons. But now it's full. Anything with more electrons than helium is going to have to use other sublevels, like lithium. So lithium is the 3rd element, so that means 3 electrons. The first 2 can fit in this first sublevel because that's at s, and s's can contain a maximum of 2. But that 3rd electron is going to have to jump up to the next available sublevel, which is the 2s. 2s's can contain up to 2, so we could still fit another electron in there if we had to. Let's try carbon. Well, the first 2 electrons can go in the first s sublevel. The second s sublevel can contain 2 electrons as well, so the next 2 can go there. But carbon's got 6 electrons in it because it's element number 6. So the next 2 electrons are going to have to go in the p sublevel. Now the p sublevel isn't full yet because p's can contain up to 6 electrons. So if I needed to, I could keep adding electrons in there. I don't need to for carbon, but for nitrogen I would. Chemists have several ways of communicating where the electrons are in a given atom. And this method of communication becomes really important when we are talking about bonding in later chapters and how chemical change takes place. Some of these models are more useful for one thing or for another thing. None of them is universally valuable. And the first one we're going to learn about is called electron configuration. Now, in electron configuration notation, we write down something in this format, N and then X, and then a number. So what do these letters stand for? N stands for the shell. So this is the principal quantum number, 1, 2, 3, 4, 5, up to infinity. X, well, X stands for what is the subshell. And here we're using the subshell's letter designation, so S, P, D, or F. And then the pound sign here, this is a representation for a number, and this is really the population in this subshell, how many electrons are there. So that's the population of the subshell. So for example, hydrogen. Hydrogen has 1 electron. That electron is populating the 1s subshell, so we would write down 1s1. So shell, subshell, population in that subshell. Helium. Helium has 2 electrons. Just like with hydrogen, they're both in the 1s sublevel. So 1s2. Shell 1, subshell s, population 2. You shouldn't read this 1s squared. We're not squaring s. This is not math. This is just a notation that we use to describe where the electron is in an atom. Carbon. Well, if you recall, carbon has 6 electrons. The first 2 of them went in the 1s subshell. S's can contain up to 2. The second 2 had to go in the 2s subshell. And then that was full. The next energy subshell was the 2p. And so the remaining 2 electrons to get up to 6 had to go there. So that's the electron configuration for carbon. Another kind of notation that's very commonly used is orbital diagrams. Orbital diagrams actually give you more information because they not only tell you what subshells are populated, but what orbitals are populated. Here's how it works. An orbital is represented by a set of parentheses. This is my way of doing it, and a lot of chemistry teachers teach this method as well. But some people use a square or a rectangle. Some people just use a line to represent an orbital. There are different ways of doing it. In this class, we're going to use parentheses. Well, an orbital can contain up to 2 electrons. Here's how we represent the electrons, with arrows. Now we have arrows that can point up, and we have arrows that can point down. The ones that point up represent a spin-up electron. The ones that point down represent spin-down electrons. The real key here, it doesn't really matter which one you use, because who knows what the spin is going to be on an actual electron in an actual atom. But the important thing is if you do have two of them in the same orbital, they have to have opposite spins. And another thing is, if you've got orbitals that are in the same subshell, like a P, for example, has 3 orbitals in it, here's how you'd write that. You'd put 3 sets of parentheses, but to show that they belong together, that they all go in the same subshell, you draw a line over the top of them. Or sometimes people draw a line underneath them. But you want to tie them together with a line to show that they're in the same subshell. And another thing that's important is, even if some of the orbitals in a P or D sublevel are unoccupied, even if they have no electrons in them, you still want to draw them anyway. You draw everything in the sublevel. All right, so let's draw orbital diagrams for hydrogen. Hydrogen is 1s1, if you recall correctly. So that means we have a 1s orbital, and it's got 1 electron in it. So we draw it like that. Helium. Helium was 1s2. So I'll draw my 1s sublevel. It's just 1 orbital, and I'll put in it a spin up electron and a spin down electron, because there are 2 electrons in it. They have to have opposite spin. Now let's try carbon. Well, carbon was 1s2, 2s2, 2p2. So let's try the orbital notation. 1s, 2 electrons in there. 2s. S's, remember, have 1 orbital, so I'll draw that 1 orbital, and this one has 2 electrons in it. 2p. Now remember, p sublevels, you should draw all the orbitals, even if they're not all full, and draw a line over them. So this represents the 2p sublevel, or 2p subshell. Now it's got 2 electrons in there. So I have a dilemma. Where do I put them? Do I bunch them both up in the same? Do I put them in the first and the second? Do I put them in the first and the third? What do I do? Well, there's a rule discovered apparently by somebody named Hund called Hund's rule. Hund's rule says basically this: electrons that are in subshells, that are in the same subshell, are going to spread out so that they can form as few pairs as possible. So another way of thinking about it is these things like to be alone unless they can't help it, unless there's no room. So let's go back to carbon and try again. Remember, it's 1s2, 2s2, 2p2. And so far we know that 1s has 2 electrons in it, and the 2s is a single orbital with 2 electrons in it, and the 2p is a set of 3 orbitals, all tied together with a line. The 2 electrons, according to Hund's rule, are going to pair up as little as possible, so they're not both going to go in the same orbital. One's going to go in its own orbital, and the second will get its own orbital. They're going to stay away from each other. The only way they're going to double up in these orbitals is if they just can't help it, and there's no room for them not to. Now, as you add more and more shells, things start to get more complicated. This is the energy level diagram as we have it so far. And so far it's a neat jump from 1 to 2 to 3, and from S to P to D. But if we add the 4th shell here, you can see that there's some overlap, because there's so much difference between 4S, which is the lowest sublevel in 4, and 4F, which is the highest sublevel, that the 4S actually gets down lower than the 3D. So if you're going up by sublevel, you go 3P, and then 4S, and then 3D. Add the 5th shell in there, and it gets even worse. There's more overlap. 5S comes before 4D, and 5P comes before 4F. If I add the 6th shell in there, it's a mess. Now, this would be really hard, almost impossible, to keep track of and memorize this chart and all this complicated structure. So there are tricks that people use. There are some memory devices and things that you can use, but I think skip all of those things and go straight to the periodic table, because the periodic table, it turns out, has exactly what we need on it. The first row, it turns out, fills the 1s shell. So here we have hydrogen, and we have helium, 1s1, 1s2. There are only 2 blocks in the first row. The second and third row are divided into 2 segments. The first segment has a set of 2 squares in it. Well, there are 2 electrons in an S subshell. The second segment has got 6 spots in it, 6 squares. And a p sublevel can contain up to 6 electrons. The next two rows, the first two columns fill the s subshell for that row, so 4s and 5s. Then the next 10 fill, guess what? The d's, because there are 10 electrons in a d subshell. Now this isn't the same as the row number because of that overlap thing. So it's 4s and then 3d, and then it goes back up to 4p. And in the fifth row it's 5s, then 4d, then 5p. The next rows get even more complicated. First you fill the s's in the first two columns. So the first two columns always fill the s's for the row number, so 6s and 7s. Then you skip down to the lanthanides and actinides. Remember, the lanthanides and actinides actually belong in between the S and the D segments here. And guess what? There are 14 columns in the lanthanides and actinides, and there are 14 possible electrons that can populate an F subshell. But that's 2 less than the row number. So if I'm in row 6, the F's from that row are actually 4 F's. And then the D's are 1 less, so that would be 5 D's. And then I'm back up to the row number when I get to my P's, and I'd have 6 P's. So row 7 would be 7S, 5F, 6D, 7P. So this pattern allows us to just read the electron configuration right straight off the periodic table. Here's how you do it. Start at hydrogen, and then going left to right, top to bottom, just like you read English sentences, write down all the full subshells, and then when you get to the last subshell, fill it right up to the target element. So let's do an example. Phosphorus. Here's phosphorus right there, and it's in the third column into this P block in row number 3, principal quantum number 3. So that's where we're going to end. Here's where we're going to start. We always start in the same place, right there with hydrogen. So filling through the first row is going to give me 1s, 2. The second row, 2 blocks for s, so that's my 2s2, and then 6 blocks here for p, so that's 2p, 6. Third row starts out with a segment of 2 blocks there, so that's 3s2. And then I'm going to get into my p's here. These are going to be 3 p's. But I'm not going to go all the way through to 6 because I'm stopping there. So 3p1, 3p2, 3p3. Everything in that column is going to end in p3. Everything in the next column would end in p4. Everything in the previous column will end in p2. And the n in front will be just the row number. So I'm in row 3, p3 block, so I end with 3p3. Try this one. I'll give you an answer in a second. See if you can do it. Okay, starting at hydrogen, I want to end up at bromine. So this is the 1, 2, 3, 4th row down, and bromine is the 5th in the P, so this is going to end in 4p5. Where does it start? It starts where they all start. First row. First row fills the 1, so it's 1s2. Second row, s and a p. So that's 2s2, 2p6. Third row, also an S and a P. A block of 2, that's the S's, a block of 6, which is the P's. So 3S2, 3P6. Fourth row. Now I have S's, and that's the same as the row number, so I start out with 4S, and I'm all the way through it, so that's a 2. Then I go through these D's. 3D, 10. And now I'm near my target. I'm going to go 5 steps into the 4p. I go back up to 4, back to the row number, and then p5. So there's my electron configuration. Try lead. I'm going to end in lead. I'm in the 1, 2, 3, 4, 5, 6th row down. So this is going to end in 6p2. Starts at the beginning. First row, 1s2. Second row is an S and a P, so I write down 2s2 and 2p6. So that gets me through these 2 and these 6. Third row, again, it's an S and a P. So 3S2, 3P6. Third row, got an S, a D, and a P. Remember, the D's are one less than the row number. The S and P are the same as the row number. So this is row 4, 4S2, 3D10, 4P6. Next, N is 5, so 5S2. Drop down to 4s to go through the D's, so that'd be 4D10, and then back up to 5 to get through the P's. Go all the way through all 6 of them, 5P6. Now I'm in row 6. First 2 are 6S. 2. Now, right here, I'm really supposed to jump into here. And I go all the way through this row. That's 14 F's, and they're 2 less than the row number, which means 4F14. Then the D's. So I'm done with this. I go back up in here, go into the D's, and I go through there, all 10 of them, and they're 1 less than the row number. I'm in row 6, so these are 5 D's, population 10. And then to get to lead, I'm going 2 steps into the 6P, and I end in 6P2. Well, that's a lot of writing. And it turns out most of the writing is not really all that relevant for chemistry. Most of the chemistry happens, nearly all the chemistry happens, in the highest shell. We call it the valence shell. So it really doesn't make a lot of sense to write down all of these letters in many cases in chemistry. So we have a shorthand. You will notice that all of the noble gases, except for helium, end in P6. The highest shell then starts after that. This one, for example, lead. P6 ends the row that starts before lead, and all of lead's highest level electrons come after that. So what we do is we take all that stuff that came before and we replace it with square brackets with the symbol for the noble gas that ends the previous row. So the noble gas that ends the row before lead is xenon. So instead of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, I just put xenon in square brackets and don't write all the rest of that stuff. And then I follow it up with 6s2, 4f14, 5d10, 6p2. So I'm only writing the stuff that's relevant for our chemistry. So just to review, in shorthand notation, we replace the first part of the electron configuration or orbital diagram. You can do this with orbital diagrams too, with the symbol for the previous noble gas, the noble gas for the row that came just before it, and the noble gas goes in square brackets. So chlorine, for example. All right, so first I want to locate chlorine. Here it is right there. I go up one row and over to the right, and that's the previous noble gas. That's what I want to start with. So I'm going to write down, in square brackets, neon. Then I'm going to follow it up with what comes after neon, but before chlorine. So that's the end of the second row. So I start in the third row. This is the S's, so 3S2. And then I'm going through 3P1, 2, 3, 4, 5 before I get to chlorine, so 3P5. And there's my shorthand notation for chlorine. Let's try iodine. This is a little farther down in the periodic table, but it's actually not much harder to write. So here's iodine right here. To find out what noble gas goes in brackets, I go up one row and over to the right and identify krypton. So I'm going to start out with krypton in square brackets. Now this is in the 2, 3, 4, 5th row that iodine is. So I start at the beginning of the 5th row. So the 5th row is 5s2. Then 4d10. Then 5p. 1, 2, 3, 4, and 5 when I get to iodine. 5p, 5. So there's my shorthand notation for iodine. Well, this gives you some insight into what's the useful part of this quantum mechanics physics stuff that helps us in chemistry. Since all the important chemical action happens in the highest energy level, the highest shell, this last notation is the most useful one that we've learned so far. Don't forget that these symbols and letters, they're just representations of regions in space where the electrons are likely to be found at any given time. The shapes of those orbitals turns out to be important in determining what the shapes of molecules are going to be. And this particle model that we're going to refer to from now on out really is a little artificial. The electron really isn't a particle. It sometimes behaves like a wave, and that's where these ideas originally came from. But most of the time from now on out, we're going to pretend that electrons really aren't waves. They're particles that have quantum numbers that describe orbitals inside shells and subshells, and the electron has either spin up or spin down depending on which direction the little particle is spinning. It's not true, but it's a way of thinking about it that works well for chemistry.